Hello students, and welcome to the second part of lecture 3 for mechanics of materials. In this lecture we are going to discuss a very important material property called Poisson's ratio. When a material is subjected to a uniaxial tension or compression, so it's very important, the uniaxial, because the force will be applied in one specific axis. It can be tension, it can be compression, but it will be just in one axis, and the body will behaving accordingly. For example, you have this blue force applied on this box, and what happens is it results in something like this. So the transparent region shows the initial position of the body, while the block shows the final position, and you can see that it has reduced in length in the longitudinal axis, or the axis in which the forces are applied, and then it has extended in the other two axes. So it has increased in length in this axis as well as in this axis. And these axes are actually termed as, wherever the force is applied, that specific axis is known as the longitudinal, while the other two axes are termed as the lateral axis. And this is very important in order to calculate the Poisson's ratio, we need to know which are the longitudinal and which are the lateral axis. Now this is in case of compression, where your length of the longitudinal axis is reduced while the lateral axis length increases. But in case of tension, the story is totally opposite. So your length in the longitudinal axis increases while the length of the lateral axis decreases. Okay, let's see, this is again the case of the tension, where we have the forces applied in the x-axis trying to elongate the body. Okay, we have the longitudinal axis as x, while the two lateral axes are ly and lz. Okay, so you are trying to pull the body and creating a tension force and trying to elongate the body. So the longitudinal axis extends but the two lateral axes actually contract. This gives you the change in length in all three axes. So in the longitudinal axis, or the x-axis, you have the change in length as delta Lx divided by 2. Divided by 2 is because it is also extending in the other direction. So it extends on both the direction. Okay, and so the total change in the longitudinal axis will be delta Lx. Similarly, the change in the lateral axis, which is Ly and Lz, are also given here. Now that we know the changes in x, y and z axis, we can actually go on and calculate the strain, and we already know the strain is actually given as change in length divided by the original length. Now it's very clear that in this case we do not have the change in length in just one axis, but we have change in length in all the three axes. We have change in length in x, in y and in z axis. Similarly, we have the original length of x, y and z axis. This gives us the strain in x, strain in y and strain in z axis. Now what is Poisson's ratio? Poisson's ratio is actually defined as the lateral strain divided by the longitudinal strain. Okay, so we now know what are the lateral and longitudinal direction. We have the change in length and we have the original length of all the three axes, and we can calculate the strain in the longitudinal axis, we can calculate the strain in the lateral axis, and this gives us the Poisson's ratio, which is the strain in lateral axis. Lateral axis in this case is the y and z axis, or the lateral axis, but the x axis is the longitudinal axis, and that is why we get the Poisson ratio as the denominator is longitudinal axis. So in both the cases you will have strain in x, and then you can have lateral axis as either y or z. It is assumed that the lateral axis strains are equal, so you can use any one to calculate the Poisson ratio of the body. Okay, very simple, straightforward, nothing complicated. Now for most of the materials, metals, the Poisson ratio stays around 0.3, 0.3 to 4, somewhere there. For the soft materials it will go to 0.5, like for example for rubber. For very hard materials like for example concrete, cork, it will be around 0, close to 0. Okay, so let's go on and try to solve this very basic problem. It states that a cubic block with each side of length 4 meter is subjected to a force shown. So force is given, and we know where it is applied. If its sides along x and y direction increased by increased to 4.0001, so this axis and this axis, so let's say this side and this side, they increase to this one. Initially is 4 meter, but now we have increase in length because of this force in longitudinal axis. Because it is compression, we know that the longitudinal axis will actually reduce in size, but the other lateral two axes, which are x and y, so z axis will reduce in size, but x and y axis, which are lateral axes, will increase in size. So we have to determine the Poisson ratio of the material. Okay, so let's go on and try to solve this basic problem, a very simple basic problem. One thing is very clear, that the material of the body is the same, which means the volume will stay the same. So first thing we need to do is actually calculate the volume of the body. It is a cube, okay, so volume will be equal to 4 into 4 into 4, okay, so the area of cross section multiplied by the height. So that is the formula for the volume of a cube, okay, and it gives you 4 4 16 16 4 64 cubic meter. This is the volume of the body. So we calculate the volume of the body initially, because after changing in the dimensions, the volume will still remain the same. Okay, once the forces are applied, we can see that this axis is reduced. Okay, so your strain in the z axis, this is the longitudinal axis, will be again the change in length of z divided by the original length of z. Okay, now we do not know this one, but the other two are given, because it says that the x and y changes into 4.0001, and it is increased, right? So let's go on and calculate those ones first. So we have the strain in x, which is the change in length of the x-axis. Initially it was 4, now it is 4.0001 minus 4. This is the change in length in x divided by the original length. Original length was 4, so you can say that it is 0.0001 divided by 4. Okay, so let's calculate this. So you have 0.0001 divided by 4, so you get 0.000025. So you get 0.000025. Keep in mind it will have no units because it is length divided by length, so you get no units for that. Now what we got is actually the strain in x-axis, and since the length of the y-axis is actually the same, so original length of the y is the same, the change in length of y is also the same as it states. Okay, so your strain for the y will also be equal to 0.4 zeros and then 5. Okay, so we got two strains. We got strain in x, which is this one, and we got strain in y. Alright, now what is left is the strain in z, but we know the volume stays the same. Okay, but we know the original length of this is 4, but we do not know the change, how much change it has got. And if the volume is the same, we can actually find out the change. Let's see, because your final volume, let's say I call it Vf, will be equal to the change, the new length, or whatever you call it. So new length of the x is 4.0001 multiplied by the new length of y, which is 4.0001, and then multiplied by the new length of z. So you can call it as L and z, or new length of z, whatever you want to call it. Okay, but we know the final volume will be actually staying the same as the original volume, which is 64. So you can make it 64 is equal to 4.0001 0 1, you can take it as a square because it is multiplying with itself, multiplied by ln z. Okay, so you can actually calculate this new length of z axis, which will be is equal to 64 divided by 4.0001 square. Okay, let me calculate this. Okay, so you get 3.9998 as the new length. So there is your 3.9998 meter is the new length for the z-axis, because we said this axis will compress. Okay, initially it was 4, now it is 3.9998. Okay, now we can actually find the change in Lz, which is actually delta Lz. So initially it was 4, now it is 3.9998. So your change in Lz will be 4 minus 3.9998 is actually 0.0002. Once we know the change in Lz, we can go on and calculate the strain that we actually could not find initially. So that will be our strain in Z is equal to the delta Lz divided by the original length of Z. So change is now we know 0. Divided by the original length was 4. So you get 0.00005. So you get the strain in Z equal to 0.0005. Now we know all the three strains. We know the strain in longitudinal axis, which is this one. We know the strain in one lateral axis, and we know the strain in second lateral axis. And we can go on and calculate the Poisson's ratio, which is very simple now, because we know the Poisson ratio is actually what? Given as the lateral axis strain, which is x or y, whichever you want to take it, divided by the strain in longitudinal axis, and it will also be equal to strain in the second lateral axis divided by strain in the longitudinal axis. Okay, so let's see, the strain in the, let's say, x is as you can see, they both are the same. The lateral axis, yes, mostly in most of the cases they are the same, so you can just take any one of them. So there is 0.25, I think it is this one. Okay, and divided by the strain in longitudinal axis, which is this one. Alright, so you get a strain of around 0, Poisson's ratio of around 0.5. So your V becomes equal to 0. Or nu, whatever you call, you pronounce it. This is the Poisson's ratio. Now this is what we got for this specific material. Now if you look back at our case, we did say that the Poisson's ratio stays between 0 and 0.5. So this is a very soft material, probably rubber or something, that is having that much of Poisson's ratio. Okay, so it actually can tell you that how soft that material is. Okay, I hope it is clear enough, and if you have any questions, please put them in the comments, and then I will try to answer in the next lecture. Okay, take care, goodbye, see you in the next lecture.